Okay, so we want to find the mass moment of inertia about the z-axis for this shape here. Now, it's a piece of sheet metal. I know it has a mass per area of 10 kilograms per square meter. Because again, what I'm going to do here is I'm going to find the moment of inertia of each piece. I'm going to basically break it up into 1, 2, 3, and 4, find the moment of inertia of each one of these about the z-axis, and then add them together. And again, I'm going to use the parallel axis theorem that tells me the moment of inertia about the centroidal axis plus mass times the distance between the axis of interest and the center squared. Okay, so we'll start with number 1. Okay, so this is a plate basically flipping around its edge. Okay, so when I have that and I look that up, it's basically 1/12 m times that distance squared, right? So it's 1/12, where my mass again is going to be that 10 times the area of this basically square, which is 0.4 times 0.4. So again, this piece right here, this is my m, okay? And then the length of that is 400, so it's 0.4 squared. So that's when I look up a plate about flipping it as opposed to kind of like rotating it. Okay, it's that should be 1/12 ml squared. Okay, uh, that is the centroidal axis, right? There is no distance between, right? The z-axis goes right through the center of that plate, so I don't need to do any sort of parallel axis theorem on this one, and I get this equal to 0.0213. Now, I'll do the same thing with that hole there, which is basically like if you think about a coin, flipping a coin. Again, with this one, the z-axis does go right through the center, so I don't actually have a parallel axis that I need to worry about on this. So I just look it up for basically a disk that you're flipping as opposed to like rolling, and you get 1/4 pi I'm sorry, 1/4 mr squared, where m is the area, which is going to be pi r squared, okay, times the 10. Again, I won't do this for each one, but again, this is m, right, which is just the area times that um, mass per unit area to get it in terms of n, because the moment of inertia is 1/4 mr squared. Now, r is, of course, 0.1. Okay, and from this I get 0.000785. So now we'll go on to number 3. Now this is kind of like a rotating plate, right? As opposed to flipping it, you're just kind of you're turning it, rotating it. Okay. Uh, now, and the axis that you're looking at here is essentially this axis. So this is your distance that we're interested in on this one. Okay. When I look up the centroidal about kind of a rotating plate, I get 1/12, and then m we've basically done before. Okay, but then instead of just 400, it's actually that 400 squared plus the other 400 squared, because again, I got both a length and a width that I'm rotating on this sort of a rotation. It's oriented differently than it was before. Now, because of that, again, I have that um, parallel axis that I need to worry about. So again, its mass is 10 times 0.4 times 0.4, and its distance away is basically to the center of that plate, which is 200 meters squared. So again, I use the parallel axis theorem on this one. I keep forgetting that that's at 12, okay? And uh, deal with the different orientation of the plate, as well as now I actually do have a parallel axis that I need to worry about. When I do that, the moment of inertia of plate 3, basically around the z-axis, is 0.0141. Okay. Oops, I looked ahead. I thought that seemed weird because I felt like this one should be bigger than number one, which it is. I just looked at the wrong value when I picked that up. And again, I know that because about that orientation, I have a bigger moment of inertia, as well as the fact that I've have a distance away from the axis as well. So for those two reasons, it's about 5 times bigger moment of inertia around that z-axis. Now, moving on to 4, which is the hole. This time, instead of flipping that disk, you're basically, that disk is rolling, and you can see it's 1/2 mr squared, where m is, again, that 10 times pi r squared, which is 0.1 squared. Okay, so that's what m equals. And then I have my r as well, which is going to be 0.1 squared. So 1/2 mr squared for a disk in that orientation. It also has a distance. So I need to take the mass of that guy times the distance. So that's 10 times pi times 0.1 squared. That's the mass. But now the distance away is the same 200. Oh man, screwed that one up. Let me. Um, 200 squared, just like that. So again, that's mass times distance squared, where that distance is from the z-axis to the center of my circle there. Okay, and then from that, in that orientation, I get a moment of inertia of 0.0141, which is the one I accidentally wrote down incorrectly last time. Now, to find the total moment of inertia about the z-axis, I add 0.0213, right? I add the plate and subtract the circles. And I've got my other plate and subtract off my other circle. And from that, I get the total moment of inertia of this guy to be one too many ones. And that will be kilogram meters squared. So again, be careful with the orientations. Again, we're just breaking them up, finding the moment of inertia, each one about the z-axis. Be careful with your orientations and, the distance away from the axes that you're looking at with the axis of interest. And make sure you subtract the holes, add the, solid pieces, and you get that answer that I have there for the moment of inertia about the z-axis of this composite body.